All right, today we're doing something really cool. We're cracking open a pretty complex engineering dossier to uncover what looks to be a modern mechanical marvel.
So, what have we got here? Well, buried inside all of this technical jargon about gear ratios and firmware lies the blueprint for a device with a truly legendary name, the Neo-Antikythera. Now, to really get the ambition here, you've got to look back, way back, over 2,000 years to its namesake. We're talking about a masterpiece of ancient engineering, a clockwork of bronze gears that literally modeled the cosmos. This new project? It's all about capturing that exact same spirit, but with today's technology.
Okay, let's dive right in. We're going to start with the device's mechanical heart. The system that gives it all its raw power and motion. The entire system is powered by this multi-barreled spring array, and it's designed to store 15 joules of energy. To put that in perspective for you, that's enough juice to lift an apple about 15 meters straight up into the air. It's a small but really dense power pack that keeps the whole device running for a full 30 minutes on just a single wind.
And those springs, they don't just store energy, they deliver it with some serious force. We're talking a peak torque of half a Newton meter. That's kind of like using a 10-centimeter wrench with a half-kilogram weight hanging right off the end. It's that powerful, consistent force that's needed to drive every single gear in this ridiculously intricate machine. Now, this is where it gets really interesting, how all that raw power gets refined. There's a 4-stage gear train that creates this massive 540-to-1 step-up ratio. What that does is transform the slow, powerful unwinding of the springs into incredibly fast, precise movement right where it counts, at the escapement. That's the timekeeping heart of the whole mechanism, and it's ticking away at 180 RPM. Just amazing.
Okay, so we've got the muscle. Now let's move to the digital brain and see how all that raw mechanical power is teamed and controlled with modern electronic precision. The whole operation is governed by a tiny, hyper-efficient ESP32C3 microcontroller. You can think of it as the low-power nerve center, managing every single calculation and command needed to keep this machine perfectly, and I mean perfectly, on track.
And this right here, this is the core of that control. It's a feedback loop that runs 100 times every single second. It uses Hall sensors, which detect magnetic fields to measure rotation, to sense the mechanism's position. Then it calculates even the tiniest deviation from perfection, and then pulse. It sends a micropulse to a stepper motor to correct the speed. It's just this constant, invisible dance of digital precision.
So we have the power, and we have the brain, but what is this machine actually made of? Because, the materials they picked are just as critical as the design itself. Honestly, this bill of materials reads like a recipe for a supercar. You've got a rigid, lightweight aluminum frame as the skeleton. For the high-speed parts, you're looking at near-frictionless joule and ceramic bearings. High-load gears are made of classic, strong brass, and the springs themselves, well, they're a special alloy called Nivaflex, which is known for its incredible energy density. Every single part is chosen for peak performance. Now, here's a crucial point. Before any of these exotic, expensive materials are even touched, the entire device gets built, stressed, and perfected in a virtual world. And these aren't just items on a checklist. They are full-on mission objectives for its digital twin. Computer simulations make sure the frame can survive those immense spring forces, that the gears will mesh without a single flaw, that any wobble is limited to a minuscule 0.3 degrees, and that any harmful vibrations are just engineered right out of the system from the get-go.
So, what happens now? This incredibly detailed Phase 1 blueprint is complete. How does it make that leap from the computer screen into the real world?
Well, this next phase is all about that transition. The engineering team will deliver the final stress reports, that's the finite element analysis, or FEA, alongside these ridiculously detailed computer-aided design, or CAD models for manufacturing. And most importantly, they'll create a really comprehensive physical test plan to make sure that the real-world prototype performs exactly as all those simulations predicted. As the dossier itself says, this is really just the first chapter. It's all the meticulous research and development that lays the groundwork for what promises to be an extraordinary piece of modern precision engineering. Which leaves us with a final, kind of tantalizing question, one that really echoes the mystery of its ancient namesake. The original was built to track the heavens, but with this level of mechanical power and digital precision, you have to wonder, what is the ultimate purpose of this incredible modern device?